Section 1. A Universe Reimagined. Today is October 24th, 2025, and we live in a world governed by predictable, understandable laws of physics. We launch satellites into precise orbits. We design bridges that withstand immense forces. We predict the paths of celestial bodies with astonishing accuracy. But this reality, this clockwork universe of knowable rules, was not always so clear. Before one man, the cosmos was a place of mystery, its movements often ascribed to divine whims rather than mathematical certainty. That man was Isaac Newton. He did not simply discover a few new facts about the world. He fundamentally rewrote our understanding of reality itself, providing a new language, the language of mathematics, to describe the very fabric of existence. His work became the bedrock of modern science, a revolution in thought that began in the quiet English countryside. Isaac Newton was a figure of immense complexity, a solitary genius whose mind journeyed to places no one had ever been. Born prematurely on Christmas Day in 1642 in the small hamlet of Woolsthorpe, England, he entered a world of turmoil, both politically and intellectually. The old ways of thinking, rooted in the ancient philosophies of Aristotle, were beginning to crumble, yet a comprehensive new system had not yet emerged to take their place. Newton was the architect of that new system. He provided the tools, the laws, and the mathematical framework that would allow future generations to build the modern world. His life was a series of profound intellectual milestones, each one a crucial step in constructing a new perception of the universe. The story of Newton is not just the story of a scientist, but the story of the birth of a new kind of thinking. It is a tale of intense focus, relentless curiosity, and an almost superhuman ability to hold a problem in his mind for days, weeks, or even years until it yielded its secrets. From his reclusive years during the Great Plague to his celebrated position as a luminary of European science, Newton's journey was one of transforming chaos into order. He looked at the falling apple, the orbiting moon, and the colors of a rainbow, and saw not disparate phenomena, but the elegant and unified workings of a single, grand design. This essay will trace the key milestones of his life, showing how each discovery contributed to his monumental rewriting of reality. We will explore his humble beginnings and his formative years at Cambridge, where his dissatisfaction with the established curriculum set him on a path of independent discovery. We will delve into his miracle years, giving rise to his initial thoughts on calculus, optics, and universal gravitation. We will examine the creation of his magnum opus, the Principia Mathematica, a book that laid down the laws of motion and gravity and established the blueprint for classical physics. Finally, we will consider his later life and enduring legacy, recognizing how his ideas continue to shape our world in countless ways, from the engineering of our tallest skyscrapers to the exploration of the furthest reaches of space. Moving on. Section 2. From humble beginnings to a scholar's calling. Isaac Newton's life began in a state of fragility and solitude, born in the manor house of Woolsthorpe by Colsterworth. He was so small and weak that no one expected him to survive his first day. His father had died 3 months before his birth. His mother Hannah was left to manage the farm alone. At 3, his mother remarried and moved away, leaving Isaac with his maternal grandmother. That separation shaped a fiercely independent, insecure personality. He preferred his own company and his own thoughts. He was not a promising academic at first, idle and inattentive. He loved building intricate mechanical contraptions, model windmills that could grind flour, water clocks that kept surprisingly accurate time, a small cart he could propel by turning a crank. He filled notebooks with drawings and observations. He studied the sun and made sundials to track its progress. When his mother, widowed again, pulled him out of school at 17 to be a farmer, Newton failed at farming, found reading under a tree instead of herding sheep. His uncle, a Cambridge clergyman, saw his gifts. With the headmaster, they persuaded his mother to send him to university. In 1661, at 18, Newton went to Trinity College, Cambridge. He enrolled as a subcizar, doing menial tasks to pay tuition. Though the curriculum relied on Aristotle, Newton read new thinkers: René Descartes, Johannes Kepler, Galileo Galilei. He filled a notebook titled Questiones Quaedam Philosophicae with critiques and ideas. So that's where it started. Section 3. The Miracle Years: Isolation, Apples, and the Birth of Genius. Just as Newton was beginning to immerse himself in the vibrant intellectual world of Cambridge, a national catastrophe intervened. In 1665, the Great Plague swept across England, forcing the university to close its doors and send its students home to wait out the epidemic. Newton returned to the quiet solitude of his family home at Woolsthorpe Manor. For the next 18 to 24 months, he was almost entirely isolated from the academic world. This period of forced seclusion, which could have been a frustrating interruption, instead became his Annus Mirabilis, or miracle years. Free from the structured curriculum and the distractions of university life, his mind was unleashed, leading to a creative explosion unparalleled in the history of science. It was here, in the quiet of the countryside, that the seeds of his greatest discoveries were sown. During this intense period of solitary contemplation, Newton began to lay the mathematical groundwork for what would later become calculus. He called it his method of fluxions, a revolutionary tool for understanding rates of change. He conceived of lines being generated by the continuous motion of a point and areas being swept out by moving lines. This dynamic approach allowed him to tackle problems that had stumped mathematicians for centuries, such as finding the slope of a curve at any given point or calculating the area underneath it. While he did not publish these findings for many years, the invention of fluxions provided him with the powerful mathematical language he would need to formulate his later theories of motion and gravity. It was also at Woolsthorpe that Newton conducted his seminal experiments in optics. In a darkened room, he allowed a single beam of sunlight to pass through a small hole in a window shutter, and then through a glass prism. The world believed that the prism somehow colored the pure white light. Newton demonstrated something far more profound. The prism was not adding color, but was instead separating the colors that were already present within the white light itself. He showed that white light was a composite mixture of all the colors of the spectrum. To prove this, he ingeniously used a second, inverted prism to recombine the scattered colors back into a beam of pure white light. A simple yet elegant experiment that decisively overturned centuries of mistaken belief about the nature of light and color. After using a first prism to split a sunbeam into its constituent rainbow of colors, red, orange, yellow, green, blue, indigo, violet, he isolated a single one of those colors, for example red, by allowing it to pass through a small hole in a screen. He then passed that isolated red beam through a second prism. Instead, the red light emerged simply as red light, refracted at the same angle but otherwise unchanged. This proved that the colors were not created by the prism, but were fundamental, immutable properties of the light itself. The prism acts not as a modifier, but as a filter, sorting the colors by bending each one at a slightly different angle. This phenomenon, which he called dispersion, explained why rainbows appear in the sky. Raindrops act as millions of tiny prisms, splitting sunlight into its full spectrum. He published his initial findings in a paper to the Royal Society in 1672. This new theory of light was so radical that it immediately drew intense criticism from established scientists like Robert Hooke, sparking a bitter and lifelong animosity between the two men. Newton's deep understanding of light and lenses had practical applications as well. Recognizing chromatic aberration in refracting telescopes, he designed and built a reflecting telescope in 1668. Using a curved mirror that reflects all colors equally, his design eliminated chromatic aberration and became the template for modern observatories. Long before the Principia cemented his legendary status, Newton's first foray into the public scientific arena was through his groundbreaking work on optics. Following his return to Cambridge, Newton's genius was quickly recognized, and he was appointed Lucasian Professor of Mathematics in 1669, a prestigious post he would hold for over 3 decades. For years, his revolutionary ideas on motion and gravity remained largely private, confined to his notebooks. The catalyst came in 1684, when Edmund Halley visited Newton. Halley was vexed by what force would cause planets to move in elliptical orbits, as Johannes Kepler had observed. To Halley's astonishment, Newton immediately replied that it would be an inverse square force, a force that weakens in proportion to the square of the distance. When asked how he knew, Newton calmly stated that he had calculated it years ago, but had misplaced the papers. Urged on and supported by Halley, Newton embarked on an even more concentrated period of work, developing a comprehensive theory of mechanics and gravitation over about 18 months. The result was Philosophiae Naturalis Principia Mathematica, published in 1687, widely regarded as the single most important scientific book ever written. It laid out a unified mathematical system of the world. At its heart were Newton's 3 laws of motion and the law of universal gravitation. The first, inertia. The second, force equals mass times acceleration. The third, action and reaction. He proposed that every particle attracts every other, proportional to their masses and inversely proportional to the square of the distance. With a single law and his 3 laws of motion, he explained planetary orbits, the tides, comets, revealing that the same physical laws governed everything from cannonballs to planets. Reality had been rewritten. Parallel to his world-changing discoveries in physics and optics, Newton was forging a new and powerful mathematical tool essential for describing a world in constant motion. This tool, which he called the method of fluxions, is known today as calculus. He began its core concepts during his miracle years, seeing it as a way to quantify change. Quantities were fluents, generated by continuous motion, and their instantaneous rates were fluxions. Differentiation found the fluxion. Integration found the fluent, the area under a curve. Crucially, he realized those operations were inverses, now known as the fundamental theorem of calculus. Despite inventing the system in the 1660s, Newton did not publish for decades. In the 1700s, Leibniz independently developed his own version with a different notation. When Leibniz published in 1684, the dispute over priority erupted into a vicious nationalistic feud. Newton, as president of the Royal Society, used his position to orchestrate a campaign against Leibniz, even anonymously drafting the official committee report. Modern historians agree Newton developed first and Leibniz published first, independent discoveries. Yet the acrimonious dispute consumed their later years and split European mathematics for a century. In the later phase of his life, Newton transitioned to a powerful public figure. Appointed warden in 1696 and master in 1699, he took the mint crisis as serious duty. Assays, rooting out corruption, going undercover to prosecute counterfeiters, stabilizing the economy with the Great Recoinage. During this London period, Newton also embraced his role as the patriarch of British science. In 1703, he was elected president of the Royal Society, and he ruled over it with an iron fist for the next 24 years. He used his authority to promote his own vision of science, to settle scores with rivals like Robert Hooke and Leibniz, and to cement his own legacy. In 1705, his status was officially crowned when Queen Anne knighted him during a royal visit to Cambridge. He was the first scientist in history to be so honored for his work, a clear signal of the rising importance of science in the national consciousness. Sir Isaac Newton had become a symbol of intellectual achievement and national pride, a monumental figure whose fame was unparalleled in Europe. Newton passed away in his sleep on March 20th, 1727, at the age of 84. He was given a state funeral and buried in Westminster Abbey, a place of honor reserved for kings, queens, and the nation's most revered figures. His magnificent tomb stands as a testament to the profound impact he had on the world. The poet Alexander Pope perfectly captured the sentiment of the age in the famous epitaph he wrote, "For Newton nature and nature's laws lay hid in night. God said, 'Let Newton be,' and all was light." Newton had not just made discoveries, he had bequeathed to humanity a new and powerful belief that the universe was not a chaotic mystery, but an orderly, rational, and comprehensible system governed by universal mathematical laws. Today, on this day in 2025, Newton's legacy is so deeply embedded in our world that it is almost invisible. The principles he laid down are the essential starting point for any student of physics or engineering. His laws of motion govern the design of every vehicle that moves, from a simple bicycle to a complex interplanetary spacecraft. The law of universal gravitation allows us to place GPS satellites in precise orbits, enabling the navigation systems in our phones and cars. The calculus he invented is an indispensable tool in economics, computer science, medicine, and countless other fields.